Okay, so statics is the branch of mechanics that deals with making sure things don't fall down. So if we're looking at a structure that looks like this, we're calling this ground case 1 for the purposes of this class, we need to examine the two supports and determine what forces are at play both horizontally and vertically to keep this 100 pounds up in the air and the structure standing. So on ground case 1, we're always going to start with this structure, and we're going to call it vector A, or support A. It's going at a 39-degree angle, and if we look at it, we first need to examine what all of our forces are doing. The 100-pound weight is trying to pull this entire structure down. Vector A, if it is holding up this weight, it has to be pulling the weight up, and by looking at the slope of the support, it must also be going to the right. So we're going to turn this into a vector, and we're going to make a scale drawing to determine what that is. So, scale drawing. First thing we always do, draw a horizontal line across our page. Probably want to start about in the middle of your paper. And then we need to make a 39-degree angle for a vector that goes up and to the right, which is going to put us into the first quadrant. So I'm going to put my protractor on here, line it up with the line I just drew across my paper, mark the 39-degree angle, and then we're going to, and I forgot to mark the point where I put my protractor down. I do that all the time. Don't do what I just did. We need a point that we can connect to that 39-degree mark. And we don't actually know what our scale is, because we don't know how long this is yet. So what I always do, I just go ahead and make this first vector 8 centimeters, and we're going to adjust the rest of our drawing to match that scale. You'll see what that means in just a second. So vector A, I have measured that to be 8 centimeters. We're always going to start with 8 centimeters. In theory, we could use anything, but my protractor is 8 centimeters long, so we'll just go ahead and use that to be consistent. This was a 39-degree angle, so let's mark that. And what we need to know to do the rest of this drawing is what is the horizontal and vertical force. And remember, we said that vector A is going to the right and up, so we need to figure out how far to the right is it going and how far up it's going, which means we need to construct a right triangle. So we're going to take our protractor, and just like we were doing with vectors last chapter, we need to put our protractor at the end and pivot it until we have a 39-degree angle right here. So using alternate interior angles that make sure this is parallel to our first line. I'm going to put a point there, and then I'm going to mark where 90 degrees is, and that's going to let me draw one side of my triangle. And now we have our right triangle. Let's go ahead and measure everything. Measurements will vary a little bit, but they should be pretty close. 1, 2, 3 centimeters. And looks like right at 5 centimeters. Okay, we have one vector completely accounted for. This is vector A. We don't know how much stress is on this beam yet, but we will by the time we're done. So ultimately what we're trying to find out is how much weight are each of these supporting to hold the structure up. So now we need to talk about vector B. Well, if vector A is going up and to the right, then vector B, well, we don't know for sure if it's going up or down, but we can tell based on whether or not vector A is going right or left. If vector A is going to the right, vector B has to go to the left. If vector B was also going to the right, this structure would just be pushing to the right with nothing going left, and it would fall over. So it has to go in the opposite direction to counteract and balance that out. So since it's going left, if we look at the slope, when we go to the left, it also goes up. So up and left, that angle is going to put us into quadrant 2. So come back to our drawing. We start at the origin again. And we need a 54-degree angle into quadrant 2. But we don't know how long this side's going to be. It can't be 8 centimeters because they're not necessarily the same length. And since we don't really know what our scale is, we just kind of picked one and started working with it. We're going to have to wait for a little bit before we determine how long this is. But we know if this goes 6.3 centimeters to the right, then vector B must go 6.3 centimeters to the left because it's got to balance that out. Everything in our drawing has to be balanced. The right will balance the left, the top will balance the bottom. And that's how it stays standing. So if we measure 6.3 centimeters to the left, and then we're going to go ahead and construct the 90-degree angle at that point. And we're just going to draw that vertical way up the page, and then we can connect our angle that we measured just a second ago. Connect it wherever it meets. That was our 54-degree angle. So referring back to the original problem, we're making this angle. And now we need to measure everything. So this is a right triangle. We know this length, so let's find our vertical component. So measuring that, about 8.5 centimeters. And then we'll measure our diagonal, or our hypotenuse in this case, about 10.6 centimeters. And this is vector B. And now we know, at least to scale, how long it is. So I can go ahead, I'm just going to go ahead and mark where the division between our quadrants is. This part's optional for the purposes of this video. I'm going to mark where that is. So this would be the y-axis if we were graphing. So we have quadrant 1 and quadrant 2. And the x-axes, the parts that are on the x-axis, the horizontal components, should balance. So this, if we were graphing it, this would be positive 6.3 centimeters. This would be negative 6.3 centimeters. They equal to 0 if you add them together. That means the structure won't tip over to the right or to the left. But we also need our structure to stay standing. So 5 centimeters and 8.5 centimeters is going to have to balance anything that goes down here. If we look back at our picture, this tripod type shape, at least it would be a tripod if it had a third leg, this structure has to lift 100 pounds. So that 100 pounds is the part that's pulling down. And I'm not going to draw this to scale, but I'm going to mark it down here so we don't forget about it. We have a 100-pound weight down here. Of course, it's not to scale, so don't worry about trying to make that to scale. But we know that the 5 centimeters and the 8.5 centimeters equals 100 pounds. And we can use that to figure out what our scale is. And once we know what our scale is, we can figure out the true amount of stress that's on these two vectors. So, 8.5 centimeters, well, I'll do them in this order. We'll do 5 centimeters plus 8.5 centimeters. If I subtract 100 pounds, I should get 0 because it needs to all balance out. So this is the point. We're going to have to do a little division, a little addition. First of all, 5 plus 8.5 centimeters. That's going to give us 13.5 centimeters. We'll add the 100 pounds to the other side. 13.5 centimeters equals 100 pounds. To figure out what 1 centimeter is, we just need to divide by 13.5. You kind of treat it like it's a variable. And this is the part where we want to be careful, because we don't want to round any more than we have to. So if you have a calculator that can store a number, and most of you do, we'll say 100 divided by 13.5. You hit enter. And that's what 1 centimeter is equal to. And rather than saying 1 centimeter is approximately 7.4074, etc. pounds, and potentially rounding and getting our number just a little bit wrong, I'm going to store it. And if you have a graphing calculator, the button is down here. It brings up this. It says answer, and then that arrow. That means we can store it as any letter we want. And I'm just going to push this button right here to store it as X and hit enter. So now anytime I hit X, it's going to spit that number back out at me. So to answer our question, how much stress is on A and B? We're going to take 8 times whatever a centimeter is. And on my calculator, that's stored as X. So I can say 8x 59.2593. Let's try to use at least 4 decimal places after the decimal. If you don't feel confident with that, then go a little bit further. It's always better to have more than less. If you have a different calculator, I'll show you how to store it on that as well. Do the same thing. Do 100 divided by 13.5 on this type of calculator. Store button's in the same place. And it brings up a menu with all these letters. We'll just store it as A for now. So answer stored in A. You can see the 7.4. Clear it away. And then let's do the other one. B is 10.6 times whatever a centimeter is. So 10.6, and I stored that as A, so I'm going to push the memvar button down here that says memory variable. That's what it stands for. Brings up the same menu. We hit A and enter. 78.5185 pounds. And then you would say that is your answer. A is supporting 59.2593 pounds of stress. B has 78.5183 pounds of stress. And that's what an engineer would be calculating to figure out exactly what the structure has to be able to support.